Hi everyone, my name's Xiuyuan and I'm a second year master student in computer science. My presentation topic is Could you tell me a story? So, namely, my project is on the topic of visual storytelling, which is to generate a story given a sequence of images. In this project, I proposed a sequence-to-sequence model utilizing visual and language representations extracted from a cross-modality transformer model. Problem statement. What does this visual storytelling mean? It is a task of multi-image queued story generation. Below is an example of image captioning. You can see that each image caption is isolated from each other. For example, sentence 1, a black frisbee is sitting on the top of a roof. Sentence 2, a man playing soccer outside of a White House with a red door. They are These sentences, they are not even connected to each other, let alone to form a story. Then what about this? Descriptions in sequence. We can see that these sentences do have some relations. Sentence 2, a man is standing in the grass in front of the house kicking a soccer ball. Sentence 3, a man is in the front of the house throwing a soccer ball up. They are linked by keywords soccer ball and man, but they still cannot form a story. What we really want is this, a whole story generated from image sequence. The disgust got stuck up on the roof. Why not try getting it down with a soccer ball? Up the soccer ball goes. It didn't work so we tried a volleyball. Now the disgust, soccer ball, and volleyball are all stuck on the roof. Actually, this is what we do every day. Our eyes catch dynamic scenes and objects and events every second. If we find them interesting and we would like to share it to our friends, we try to construct a story. Now we want to give the machine the same power so that they are able to do such things. This is an interesting area combining computer vision with natural language processing. On the vision side, processing from single image to images in context allows us to begin to create an artificial intelligence that can reason about a visual moment given what it has already seen. On the language side, progressing from literal descriptions to narrative helps to learn more evaluative, conversational, and abstract language. There are two main challenges. First is cross-modal. It means that machine learning training set consists of more than one single mode of data, for example, text, images, and audios, etc., and they are simultaneously trained. It is possible to find a perfect representation for one modality, but converting it to another modality is challenging. Generating the content of one modality given the data from another modality is even more challenging. The second challenge is multi-dimensions in reasoning. The information inside of an image is spatial, and relations between images are temporal. Our model needs the capability to handle both of these information distributions. So the Parawork overview, I would like to classify them into two categories. Category 1 is to process image into visual representations and then decode them into a story. In this example, hierarchical photo scene encoder for album storytelling. They first get image representations from a CNN model, and given the fact that unlike the continuous video frames, the adjacent frames and sequence of photos might be quite different. So they add a photo scene encoder here. And in addition to this, they add a reconstruction layer at the end of the model so that so that the story generated will be more smooth. But no matter how complicated model is, the first thing they do is to convert images into image representations. The second category is process images into language representations and then decode. Look at this example model. Here they first use faster RCN to detect regions of images, and they construct a scene graph based on this, based on the object detected and their positions. Next, they apply GCN and TCN, namely graphic convolutional network and temporal convolutional network, to encode the scene graph. And after that, they use a hierarchical decoder to generate the story. Again, no matter how complicated a model is, the first thing they do is to convert images into a graph that only contain language tokens. So limitation of these pyrolegs is clear. Encoding images into representations with only one modality might lose information in future processing. Here we have two ways to solve them. The first possible approach is to encode images into cross-modal representations, which is vision and language representations. The second possible approach is to do the cross-modal representation and text generation all at once with a huge model like transformers. Recent research on transformers with multimodal learning shows that partially because transformer model has surplus parameters, they can be directly applied in multimodal learning. It seems true that one transformer is enough to complete tasks on the span of two modalities. OSCA, Object Semantics Aligned Pre-training for Vision Language Tasks, is the one which achieves the best performance. They use text, label, image triplet as the input of the transformer. They are mixing contents from the different models in the input level, and the result shows that the self-attention inside the transformer is enough to learn the cross-modal knowledge without too much modification. This model achieved solid results on image captioning, text, image retrieval, and visual question answering. But here we are not able to apply transformer directly because we have a sequence of images. If we follow the same methods here, the input will be too long for transformer to handle. So this is our proposed approach. We first extract regions of images and their corresponding labels using faster RCN. Then we feed the extracted RIs in regions of images into cross-modal transformer, which is OSCA model, to get the vision and language representation. At last, we decode language representations to generate a story. The first step is to run faster RCN. You can choose any convolutional neural network as the backbone of RCN model. Here we choose ResNet 101 because OSCA, that cross-modal transformer, is using it. Here we also need to add a hook into the model so that we can get the regions of image representations along with their labels and confidence. It is worth mentioning that fast RCN trained on visual genome dataset performs better than the one trained on COCO dataset because visual genome has 1,600 object classes while COCO only has 90. The second step is to run image captioning with OSCA. Here we will try to generate an image caption with this transformer, but we will discard the captions. What we need is what we need here is the representation of the CLS token, which is used for the training of alignment of region features in word tokens, and it can be seen as the visual and language representation. At last, we perform a sequence-to-sequence model to generate story. Here we choose the bidirectional LSTM as each encoder and decoder. I'm still constructing the sequence-to-sequence model, so my current results are not convenient to show. There are only intermediate results like 60 gigabytes of image region representations. I also have an idea to modify the cross-modal transformer structure so that it can handle visual story generation. Though it is very complicated, but I still would like to try if I have time. So conclusion. In this project, I did comprehensive research on visual story generation and image captioning, and with the help of Harish, a PhD student in Professor Kabadia's group, I proposed a novel approach to generate stories from a sequence of images. That's it. Thank you.